All right, everyone. So in this video, I'm going to be going over the condensed Unit 4 practice exam here for our COVID-19 situation. But I'm sure that this video is going to get a little on the longer side because I'm going to go through each individual problem and sort of the thought process behind each one. So if you're doing the practice test or looking at the review sheets and you're like, ooh, it's just this one area that I need help with, feel free to skip around through this video. You don't have to watch every single question if there's ones that you're certain about. So we're gonna go ahead and get started, obviously, with number one. And so with our first question here, we are told that we're looking at the definitions sort of the systems and the state functions. So we're given that, the category here of what we're looking at. And so just very basic question, sort of definitional. During a thermodynamic process, we have some answer choices. So it's just basic question, think about a thermodynamic process, and let's define some of these things. We're told A, all of the state functions must increase or stay constant. B, all state functions must stay constant. C, some state functions may increase, others may decrease, and some may stay constant. Or D, all state functions must change. Now, with this question, the first thing we want to make sure we understand is the difference between what that path versus state function is, okay? So remember that a path function, it's going to matter what happens along the way, right? So depending upon what is changing in the path of your reaction, it's going to matter. But a state function is only focused solely on the beginning and the end, or the reactants and the products, for example. And those are the only two things that are going to concern us because we're just looking at the state of the reaction, not how it got there. So in a reaction, what way we can think about this is just ask ourselves, in that reaction, does the state always change? For example, can there be a reaction where you react two liquids together and it stays a liquid? That's entirely possible. Now, it's also possible that a reaction happens where you have maybe two solid things and they turn into a liquid. So that's a state change, right? So some could change, but some don't have to change, right? So that's at the reaction level. But if you think about each of the individual things that are state functions, the enthalpy, for example, right? If you're looking at the enthalpy, some enthalpies can change, right? In a reaction, sometimes the enthalpy can change. Sometimes in a reaction, the enthalpy doesn't change. Sometimes it goes down. Sometimes it goes up. It's all dependent upon what's happening. But so if we're looking at these answer choices, right, to state that all of the state functions must increase or stay constant, that is a very drastic claim. So we can automatically get rid of that one. To state that all functions must stay constant, again, very drastic claim. C says some state functions can increase, decrease, others may stay constant. Now that's a very broad claim, right? That's a very general statement. So we're going to keep that one in our bank. And then to say all state functions must change, again, very bold claim, and that's not going to be true in every situation. So we can isolate that one down to answer choice C. Awesome. Looking at number 2, we have number 2 here. Which of the following statements is true? We are first told, work is the concerted flow of energy and is positive when it is done on the system. Now, if we're just looking at that statement, right, if you look at the other ones as well, you can kind of see a bit of a pattern just by glancing, right? We can see here in A and B, work heat, C and D, work heat. We see in all 4 of the answer choices, we have this word concerted. We'll talk about that in a second. We then see in A and B, C, and D, all of them mention positive, okay, so a positive change. And then we have this last part down here that changes. A and B says done on the system, C and D says done on the surroundings. So we want to think about what's happening to work and heat in regards to the system and the surroundings, okay, and how positive plays into that. So, first we have this word concerted here. We know what work and heat are, right? But if we have this word concerted here, so that's going to be a bit of a difficult thing to understand, right? If we don't know what the word concerted means. So we're going to try to make some assumptions, about what that word could mean in the context of this sentence, okay? The word concerted, in case it comes up on the exam, is meaning coordinated, okay? So the word coordinated or organized, right? So the organized flow of energy. Okay, so let's think of that first part as organized or coordinated. And then we have this statement, is positive when it is done on the system, or is positive when it is done on the surroundings. Okay, so the first thing that we want to understand with this, right, is the difference between these two things. And so with this last statement here, positive when it is done on the surroundings, that's the first thing that should give you a hint, hey, that's actually not going to be right, because this concept of the value being positive when it is done on the surroundings is entirely incorrect. Okay, when work or heat are provided to the surroundings, that value is negative. Okay, so that automatically eliminates answer choices C and D. Okay, so then we have these two here left, A and B. We have work when it is done on the, is positive when it is done on the system, or heat is positive when it is done on the system. Now, both of those statements are correct. If you just think about work and heat and positive on the system, right? That's correct. But then we still have this very important word, concerted, okay? Again, coordinated, organized. So the difference to remember between heat and work is that work is valuable. Work is usable. Heat is extra. Heat is unusable. Heat is not productive, okay? So because heat is not productive, we're gonna eliminate heat in that idea of being organized. So we can choose answer choice A. Awesome. Now moving on to number 3. We have here, consider the following specific heats: copper, lead, water, and glass. If the same amount of heat is added to identical masses of these substances, which substance attains the highest temperature? Okay, so looking at the question first, we're told we have identical masses, right? So identical masses, so no difference in mass, everything has the same mass. And we're looking for which one is going to gain the most temperature, right? We want to see which one ends up at the highest temperature. So if we look at our values here, right? What I first did when I saw this was look at, okay, there's a pattern, right? What's the pattern? We see that lead is the lowest, right? Lead is the lowest number here, so I just put that as a number 1. Copper is a little bit higher than that, so I put that at number 2. Glass is a little bit higher than that, so I put that at number 3. And water is really high, so I put that at number 4. Okay, so if we kind of like list those out, if we see our, we have here our lead, copper, glass, and water, right? Then we want to think about, okay, what do these numbers mean? What is specific heat? What does that tell us? And the cool thing is we can actually look at the units, right? If you're struggling to remember, what's specific heat, look at the units, okay? The units tell us that it is this number, 0.384 joules. So it takes 0.384 joules per gram degree Celsius, okay? So it takes this many joules to change 1 gram 1 degree Celsius, all right? So if it takes a very small number of joules to change the 1 gram 1 degree Celsius, and if it takes a very large number of joules to change 1 gram 1 degree Celsius, then between these two substances, the one with the larger number is going to need more energy put into it in order to obtain the higher temperature. So if they're all getting the same amount of heat, that same amount of heat is only going to make this high number rise a little, but that's going to make this small number, that temperature, rise a lot. So in a scale here, we have the least increase in heat, the least specific heat in number 1 in lead, and the most specific heat in water, right? So if we have the least heat here that's necessary to raise this temperature, then that means that if with the same amount of energy, this lead is going to get the hottest, while the water is going to remain the coolest. Therefore, we choose answer choice D. Okay? All right, number 4. We are told which of the following statements is or are true concerning the first law of thermodynamics. So in terms of just like remembering what's the first law of thermodynamics, remember it's a very simple little equation, okay? If you remember this little equation, you're gonna be set because it tells you a whole lot of things. U equals Q plus W, okay? So we wanna remember U is the energy of the universe. Q is the heat, and W is the work, okay? So looking at these 3 statements here, we're told, number 1, the internal energy of the universe is conserved, okay? So we wanna think about, okay, in the universe, is energy changing, right? Is the energy disappearing and reappearing anywhere? Okay, we can answer that question with a no, right? Energy is not just disappearing or just appearing out of nowhere. It's conserved. It has to come from some place. So this statement right here is true. Number 2, we're told the internal energy of a system plus that of its surroundings is conserved. Now, if we think about the universe, right, and in terms of a reaction, right, if you've got a reaction happening here in this little container, and you've got all the surroundings around it, right? If energy is happening here, right? If energy is being created here, then that means that some energy is coming from here. Or if energy is being created out here, then that means that it is moving in here, right? So vice versa. Either way, the energy or the heat, that should be a positive, within the system is going to be the same as the heat, but opposite of the outside the system. So that means that the energy, right, needs to be conserved. The energy change of the universe, again, needs to be 0. So yes, we're gonna conserve that energy. None of it's just disappearing. Then the last one says the change in internal energy, delta U, of a system and its surroundings can have the same sign. Now the thing that goes against, right, is what we just talked about, how the energy inside is the same as the energy outside, but they have to be the opposite sign from one another so that we conserve that amount of energy within the universe, okay? So those numbers have to be opposite of one another, which makes us understand that only 1 and 2 are gonna be correct out of these 3 statements. All right, moving on to number 5. Number 5, which of the following is not a definition of internal energy or change in internal energy? Okay, so we're looking for, number 1, big word here, not a definition of internal energy or change in internal energy, okay? So first thinking about like, okay, what does that mean? What are all the variables a bit with related to energy, okay? But let's look at our answer choices, see which ones we can eliminate. A measure of the spontaneity of a reaction. Now, there should be a very big clue here. It's this word, spontaneity, right? We've seen that word before, and that word should automatically, every time, make you think of delta G, okay? Delta G, remember, is going to tell you if your reaction is going to be spontaneous or non-spontaneous. That spontaneity is not related to the internal energy. That's not a definition of internal energy, okay? They're connected, but that's not the definition. B, we have the total energy content of a system. The total energy content of a system, right, referring to the internal energy. I think that one's pretty straightforward, so we can say that one's a true statement. C, the sum of the heat and the work. Now we can think back to just what we looked at on number 4. The sum of the heat and the work is equivalent to U, right? Remember the heat or the energy of that system. So boom, we also kind of just defined for ourselves, this is describing the energy of the system. And then D, a measure of the change in heat of a system at constant volume. The measure of the change in heat, that should make your mind go to delta H, change in heat, which we remember is the same as Q at constant volume, meaning that we can use this equation, Q equals MCAT. Okay, and again, yeah, this is describing the internal energy of the system. That's how we solve for the number of the internal energy. So that's also a true statement, meaning that the only one that's not a true definition is going to be that letter choice A. Okay.